we're in mid-universe here, and as the not-so-old saying goes, you ain't seen nothing yet. There's a lot more expansion to come. But at the moment, let's recall where we are in the when we're in the early 1950s, when there's a rivalry between the Big Bang theory of Gamow and his collaborators that stalled in the late 1940s because of a lack of a theory of nucleosynthesis. We've got the steady-state theory of Hoyle, Bondi, and Gold that has successfully accounted for nucleosynthesis by the early 1960s through the theory of Fowler and the Burbridges. Meanwhile, in the background, George Ellery Hale has not been quiet. We left him with the 100-inch telescope installed on Mount Wilson. He immediately began, that's a bit of an exaggeration, actually, because World War I and his attempts in in the 1920s and 30s to organize American academic scientists as a national resource. We'll talk about that later. But he became aggressive about building a 200-inch telescope. Carnegie had pretty much enough by this time of funding telescopes, and so he turned to Rockefeller. They didn't want to collaborate with the Carnegie Institution, and they wanted their own place. And so they wound up in loose cooperation with the Carnegie Institution, building another observatory in Southern California on Mount Palomar, where a 200-inch telescope was prepared during the 1930s, a major task to make such a mirror, a 200-inch mirror, and to have the surface be as perfectly shaped as is necessary. And because of World War II, that telescope did not go into operation until 1949. Hubble, by now a somewhat senior astronomer, was made director and given privileged access to that telescope, but in fact he almost immediately retired, then died shortly thereafter, and his successor was a protege of his named Alan Sandage, who inherited what might be called first dibs on the 200-inch telescope, which he had for essentially the rest of his working life as an astronomer. Quite an enviable position. He also inherited the mantle of Hubble, of defending Hubble's view of the universe and the way that Hubble estimated distances in the universe. Fortunately, he inherited a person as well, an astronomical, it's difficult to know what to call him, craftsman, technician, not a professionally credentialed astronomer, but a brilliant astronomer who had worked with Hubble from the beginning and who worked with Sandage for the rest of Sandage's career, a fellow named Milton Humason. And already in the early 1950s, Sandage revisited Hubble's calculations and kept pushing the age of the universe back. So that by 1960, it had gotten up to approximately 11 billion years and was climbing. Eventually, Sandage would announce an age of somewhere between 18 and 20 billion years for the age of the universe, which put him in substantial rivalry with a younger generation of astronomers who argued that Hubble's technique for measuring, and the one that Sandage felt committed to improving upon but maintaining, was incorrect. And this rivalry in the 1980s and early 90s became quite nasty personally on a number of occasions. But finally, in the late 1990s, around 1998, 1999, a team of astronomers using the Hubble Space Telescope, led by a woman astronomer named Wendy Freeman, pretty much established to everybody's satisfaction that the universe is 13.7 billion years old, give or take a couple of 100 million years. And Sandage seems to have accepted that. That's just background information. We want to pick up the story of what happened to the steady-state theory, which looked like it was poised for triumph in the early 1960s. Well, two things happened to it on the way to success. One was called quasars, and the other was the microwave background radiation. One was really a kind of a misunderstanding, and the other was the killer of the steady-state theory, and it made the Big Bang theory. In 1958, Jeffrey Burbridge, who apparently had some spare time from his work on nucleosynthesis theory, was noticed that radio telescope observations had revealed that there were startling sources of energy pouring out of very distant galaxies. that they were equivalent to the amount of energy of 1 million or more stars was pouring out of the most distant galaxies that the radio telescopes were collecting signals from. Between 1958 and 1960, 1961, these phenomena were studied in some detail, including by a Dutch physicist named Martin Schmidt, who gave the name quasar to these objects, standing for quasi-stellar radiators. That is to say, these objects are relatively compact by galactic standards, only a couple of thousand light years across, and yet they have the energy of millions of stars. They seem to be associated with the centers of very distant galaxies, and they're all way out there. This is bad for the steady state. The steady state says the universe is pretty much the same in all directions and at all distances except for local variations. And yet here was a phenomenon which only existed long ago and not more recently. So if quasars, in fact, are way out there, and every galaxy that had a quasar in it had a very high redshift, which means it's way out there, it's very far away. Very far away means very far back in time. So this is an asymmetry between the early universe and the more recent universe, which suggests that the steady state theory is wrong. Now, to jump ahead, it turns out that quasars are black holes. And that every galaxy has a black hole at its core, including our very own Milky Way. Has a massive black hole which has the mass of 1 million or more suns at its core. But at the time, in the 1960s, it seemed as though the only quasars that were detected were very far away, and that was one blow against the steady state theory. The second was, so you could say, well, you know, that was a misunderstanding, and if that were the only blow, we could resurrect the steady state theory. But the second blow was the telling one, and that was the microwave background radiation. A lovely story. In 1949, Gamow and his pals predicted that if the Big Bang theory is correct, right? No, the theory's in a sense stalled because they can't explain how to build up the elements yet. Nevertheless, Gamow and his team predicted that if the Big Bang is correct, then as the universe cooled, the initial extraordinarily high frequency energy should have dropped off to microwave frequencies, and that the entire universe should be bathed in the glow of that explosion at a microwave frequency corresponding to a temperature of about 5 degrees above absolute zero. That all of space should be warmed. It should not be at absolute zero. It hasn't reached absolute zero, may never reach absolute zero. But in fact, it cannot reach absolute zero, according to quantum theory. But the average temperature, so to speak, of space in all directions, completely uniform, because if the universe started in a single spot, although there was no space at the time, then everything, the space should be uniformly filled by this radiation, which nowadays should be detectable in the microwave range, and it should be convertible into those microwaves, the energy of those microwaves should be convertible into a temperature of about 5 degrees. Well, with the sort of comatose state of the Big Bang theory during the 1950s, nobody paid attention to this prediction. It's difficult to say that somebody in South Dakota was not paying attention to it, but effectively nobody paid attention to it. But with the success of the nucleosynthesis theory by Fowler and the Burbridges, for which they received the Nobel Prize, Hoyle was not included in that. Sometimes interesting why the Nobel Prize Committee includes some people and leaves some people off. They don't like to give the prize to more than 3 people, and in fact, I don't know that they've ever done that. That would be one thing, but it would have been easy to leave off Margaret Burbridge because they had prejudice against giving the prizes to women in any event. But Hoyle had become involved in a public controversy over his commitment to the view that the origin of life on Earth was extraterrestrial. And that was considered embarrassing by a number of scientists. And so it's not impossible, we won't know it yet until the deliberations of the Nobel Prize Committee, which are kept secret for 50 years, are revealed. But it's possible that that was a reason that militated against Hoyle being left off, even though he started the whole thing by recruiting Fowler and the Burbages to work on nucleosynthesis. Anyway, here we are in the early 1960s, and nucleosynthesis is in, and a physicist, a brilliant physicist at Princeton, Robert Dicke, decides it's time to revisit the Big Bang Theory, because if we've got nucleosynthesis, in spite of the fact that it supports steady state, it also supports, maybe this is the key to the Big Bang. And he has a group of graduate students, two in particular that I want to call attention to, although it's probably unfair to some of their colleagues that these two happen to, so to speak, make it bigger than the rest, Jim Peebles and Dave Wilkinson. He put Peebles to work on re-examining this nucleosynthesis and Big Bang question. And Peebles worked out for himself the microwave background prediction. This is in 1962, 1963, and came up with a figure of, well, the energy of the microwave should be about 10 degrees Kelvin. Now, it is accepted by all historians of this that Peebles, a man of high integrity and high achievement, had never read the Gamow papers. He subsequently admitted that as a graduate student, he should have done it. He didn't do it. He just got caught up in solving the problem for himself. And so it was news to him later to discover that Gamow's team had already made such a prediction. I said they predicted 5 degrees. Actually, in several different papers, they had figures ranging from 5 to 25. They didn't know exactly what parameters to assume. Peebles came up with this 10-degree figure, and then he and Dicke and the other members of their team, astrophysics team at Princeton, started thinking about, well, how would we actually do this experimentally? Meanwhile, back at Bell Labs, there were two physicists, Arno Penzias and Robert Wilson, who were assigned the task of developing an antenna that could communicate with satellite telecommunication satellites. Now, there weren't any telecommunication satellites to speak of, but Telstar was about to be launched, and then we needed to be able to communicate with that. There had been a predecessor of Telstar called EchoStar that was launched in 1960. EchoStar was essentially a mylar balloon, and you could bounce radio signals off EchoStar, but it was just a dumb balloon. It didn't have any electronics or anything in it. Now, so that means you really have to have a super sensitive antenna to pick up those bounced off signals. They're not going to be received, amplified, and retransmitted. They're just going to bounce off the balloon. And so Bell Labs had developed an extremely sensitive antenna, and Penzias and Wilson started their work for Telstar with that antenna. It makes a lot of sense. And so setting up the antenna, they've got to calibrate it. They want to make sure that they've got a baseline of, this is neutral, no signal being received, so that when they point it at the satellite and they get a noise, they say, oh, that's not a noise, that's the signal. Well, they discovered that no matter what direction they pointed this exquisitely sensitive microwave antenna, because Telstar was going to be broadcasting in the microwave range, no matter what direction they pointed this microwave antenna, they kept getting the same hissing sound, which, they didn't do it at the time, which turns out to correspond to an energy level for the microwaves of about 2.73, if you're really a nitpicker, 2.728 degrees above absolute zero, 2.728 degrees Kelvin. They were not doing physics. They were not interested in the Big Bang, but Penzias, they got the Nobel Prize for this anyway, Penzias read the journal, the physics journal, in which Peebles' article was published predicting this microwave background radiation. And he told Wilson, I think we found it. So they called up Dicke at Princeton and said, we've made the following observation. Does it make sense to you? Unfortunately, to Dicke and Peebles, it made too much sense. They were scooped. And Penzias and Wilson, as I said, were the ones who got the Nobel Prize and established the existence of the microwave background radiation, which resurrected the Big Bang Theory in a big way, because this was an extraordinary experimental confirmation of a prediction made by that theory that is not part of the steady state theory. In fact, studying the microwave background radiation since that time, and in particular through two satellites launched by NASA in the early and late 1990s, has given us our oldest picture of the universe. We have, through the Wilkinson Microwave Anisotropy Probe, WMAP satellite, the WMAP probe, a picture of the universe as it existed approximately 380,000 years after the Big Bang, which is quite extraordinary. Now, that's a colossal understatement. Let's go back to the prediction of the microwave background radiation. Gamow's prediction was that the background radiation would be uniformly distributed. It would fill space to the same amount in all directions. By the mid-1960s, it was understood that this couldn't possibly be correct, because if that were true, then matter would never have clumped together to form stars, let alone galaxies. There are stars in galaxies. Matter did clump together, and so that means there must be extraordinarily subtle non-uniformities in the microwave background radiation. If the microwave background radiation is really 2.728 degrees in all directions, the theory is a total failure, because it cannot account for why there are stars and galaxies. The universe would have lots of atoms floating around in it, but they would all be dispersed uniformly. The word anisotropy in the name of that NASA satellite, the first one had a much nicer name, the Cosmic Background Explorer. That's easy, COBE. But WMAP is a little ungainly. But Dave Wilkinson, that second graduate student of Dickey's, he was assigned the task of looking into the uniformity of the microwave background radiation. He made that the study of that radiation and the study of the non-uniformities in that radiation, the anisotropy, the fancy name for non-uniformity, his career focus. And so NASA named that satellite after him. That's what's called the Wilkinson Microwave Anisotropy Probe. And Wilkinson established, using the satellite data, the first satellite, not as sophisticated, not as sensitive in its detection equipment as the second one, that in fact there are non-uniformities. These have been mapped, graphed. You can see beautiful pictures of them, and on the internet. The difference in temperature is in the 10 to the minus 5 degree range. But there are variations in temperature that, in fact, correspond to the clustering of matter into stars and galaxies. Well, really galaxies, into galaxies. So the microwave background radiation was a major achievement in not only resurrecting the Big Bang Theory, but in making the Big Bang Theory the theory. So now we've got Big Bang. But it turns out in the 1970s and early 1980s that quantum theory does not allow us to extrapolate the Big Bang back, or maybe interpolate's a better word, we're going backwards, to go back to the beginning using what you might call Gamow's version of the Big Bang. That the universe cannot have simply evolved from a big explosion of a compact mass of matter. That can't possibly be correct. And so there is a need to understand the origin event much more using quantum mechanics at a much deeper level than Gamow's initial hypothesis. It is broadly speaking correct, but what Gamow meant by the Big Bang, the kind of, let's just call it ordinary expansion, could not have given us the universe as we see it. That can't be the case. In 1980, a young physicist named Alan Guth, who at that point had not yet held a tenured faculty position. He had moved around the country from one postdoc to another postdoc, clearly highly intelligent, but not quite able to settle down, find a niche at any particular, to do enough to make any university make him the kind of an offer that was better than the next postdoctoral fellowship that he was that he was offered. And he had a very patient wife, as far as I can tell. Alan Guth announced a modification of the Big Bang Theory, which is, it's the kind of thing you wonder, how can anybody say this with a straight face? But Guth announced what he called inflation theory, that building on an idea by a Harvard physicist named Sidney Coleman that had been published in 1968, that quantum theory, the quantum theory of the vacuum, suggests that you can have something that he called a false vacuum, that you can have a situation in which it looks like there's a vacuum, but there's a tremendous amount of pent-up energy that is sort of stalled and can be triggered and released. Building on this idea, Guth proposed that at the ridiculous number of 10 to the minus 35 seconds after the real Big Bang, there is no matter at this point. The universe underwent an effectively instantaneous inflation in which its size doubled 100 times. In the process, the universe cooled dramatically. Like the universe at that point had a temperature of about 10 to the 28th degrees Kelvin. This is extremely hot. You would not even bother to drop an egg to boil into water that was 10 to the 28th. I'm just being facetious. The 10 to the 28th, can you make any sense out of, ordinary people can't make any sense out of that number. You can't say a million degrees, whatever. 10 to the 28th degrees Kelvin. It went through this, underwent this expansion, which pulled the universe into essentially a uniform mode with very modest non-uniformities. And into that universe, we then had the unfolding of the breaking of the symmetries that we described in an earlier lecture that led to, and I'll give you a chronology on this soon, that led to the emergence of photons and then matter. It's the inflationary moment that we're interested in here. It happened effectively instantaneously at 10 to the minus 35 seconds, powered by this false vacuum. That the energy of that false vacuum was released, and Guth showed that the way that it would be released would be to cause this inflation. So he says, okay, so the universe is very big. At the time that this happened, the universe was the size of a grapefruit, or I prefer a softball. In 10 to the minus 35 seconds after the Big Bang, the universe was about the size of a softball, and it then expanded to 2 to the 100th power. Now, maybe that doesn't sound like very much to you, but it is enough so that the entire thing we now call the universe, 13.7 billion light years, is just a minute patch on the real universe, the inflated universe, which we will never, perhaps, be able to have any interaction with. As enormous, as mind-bogglingly vast as we think the universe is, now that we know that it's made up of billions of galaxies with billions of stars, so forget it. It is a local patch on this inflated universe. You take that softball, 2 to the 100th powers in size, and 13.7 billion light years is nothing. So this is a very different universe from what we have been talking about. Since 1980, the inflationary theory of the universe, which, as you might imagine, was not initially greeted with universal acceptance, has become the orthodoxy within cosmology, within astrophysics and cosmology, that this was perhaps the critical moment in the history of the universe, and the inflation and the breaking of symmetries that we talked about in the lecture on the unification of the forces of nature are consistent with this model that maps onto the microwave non-uniformities. So that there is, while you can't do experiments on this yet, you can't make a universe in your basement or even in a very well-equipped laboratory, the available empirical evidence is consistent with this theory. That would be amazing, except since 1980, there have been two comparably dramatic developments which require reconceptualizing what we mean by the universe, even the inflated universe. That's still there. I'm not going to undermine that. The first was the recognition in the 1980s that an observation made by a brilliant but sort of cranky astronomer named Fritz Zwicky in the 1930s was right. Zwicky had observed that, you know, galaxies rotate fast enough. You can apply the Doppler effect principle to studying the motion of galaxies, and you can see that galaxies rotate. So the Milky Way being a nice spiral galaxy, about 100,000 light years in diameter. The Earth, our solar system, is about 30,000 light years out from the center. So the radius of the Milky Way is about 50,000 light years, and we're about 30,000 light years out from the center. Not on, it's a spiral galaxy, but we're not on the one of the spiral arms. We're on a little bridge of stars and gas between two spiral arms. So it doesn't seem like what you might call a prime real estate location in interstellar space, but yet here we are, and you know, we may yet have the last laugh on all of this. The Milky Way rotates. It's a spiral galaxy, and it rotates, and because we can see other spiral galaxies. How do you know a galaxy rotates? You use this Doppler effect by analyzing the light spectra. Do the same thing from the sun to see how the sun rotates, and we can actually do this with distant stars and study their rates of rotation. Zwicky said, galaxies rotate too fast to hold together. They haven't got enough gravity. You may think a galaxy is pretty big with 1 billion or more stars, or even 100 billion stars. Forget it. It hasn't got enough mass. It should whirl apart. There's got to be something that's holding galaxies together. Well, he said that in 1939, and I think you're pretty safe to say nobody paid attention to him until the 1980s, when a younger generation of astronomers took themselves much more seriously and said, you know, galaxies not only rotate, and that's a problem, but what was really discovered, and I don't want to be facetious about it, wasn't just that they were younger. They found that galaxies cluster. Not only do stars cluster in galaxies, but galaxies cluster. In fact, the Virgo cluster, for example, is made up of 10,000 galaxies. And the question is, what holds that together? What was postulated and what is, at the end of the 20th century, accepted as the consensus view is something called dark matter, which we have never observed, except that it accounts for the gravitational integrity of galaxies and galactic clusters and the clouds of gas that are known to surround galaxies. So dark matter. But what's interesting is that dark matter by the early 1990s was understood to account for over 90% of the matter in the universe. That means that our entire visible universe, made up of the kind of matter we know and love, everything we can see out there, even in the inflated universe, is less than 10% of what's really out there, because over 90% of what's out there, which may be fascinating if we could see it, who knows what they're doing, may be more fun than the producers. It's dark. And we only know about it indirectly through its gravitational consequences. So that was quite startling. Initially, this sounds like science fiction. But in 1998 came what some physicists say was the discovery of the century, in spite of everything I've said before. Two teams who do not like each other very much, Robert Kirshner at Harvard and Saul Perlmutter at the University of California, Berkeley, announced that not only is the universe expanding, but it's accelerating. The expansion is accelerating. The acceleration kicked in when the universe was about 7 billion years old. Until then, the acceleration had been dwarfed by the force of gravity that was pulling it back. But as the universe expanded to a point where the force of gravity dropped off, then the acceleration, which actually was right there in the general theory of relativity from the beginning. If you go back and check your notes, it was there from the beginning. The universe is accelerating in its expansion, which has serious implications for the future if you take a long view in your investment strategy. In the next lecture, we're going to talk about how we know all this.